Okay, so previous videos we went through a lot of math, and so I want to take the time to kind of summarize what we learned from doing all that math. Okay, so once again, consider the case where we have some sort of system where we have one chemical species and it exists in two separate phases, right? So an alpha phase and a beta phase. If it helps you visualize it better, you could think of the alpha phase being like liquid and the beta phase being a vapor. Right? And so we find that these two phases will be able to coexist with one another when the following criterion are met. When the temperature in both of the phases is the same, so T alpha is equal to T beta, right? And so that just means the total temperature of the entire system is the same. And then by minimizing the Helmholtz energy with respect to volume, we found that the system pressures also need to be the same. P alpha needs to be equal to P beta. And then by minimizing the Helmholtz with respect to N alpha, we found that the system molar energies also need to be the same. G alpha needs to be equal to G beta. Okay? Right? And so all three of these things need to be the same in order for us to have a system in which the alpha phase and the beta phase exist at the same time. Okay? All right, and so we can even simplify this down a little bit further because we know that the molar Gibbs energy is a function of pressure and temperature anyways. And so we could just say, we could sum up all these criterion into one equation, where we just say that the molar Gibbs energy of the alpha phase at some temperature and pressure is equal to the molar Gibbs energy of the beta phase at that same temperature and pressure. Okay? Yeah, so that's what we find, if this criterion is satisfied, that's when we find that both the chemical can exist both in the alpha and the beta phase. Okay? All right, so we did this mathematically, but let's try and visualize what's going on. What does this actually all mean? And so I'm going to re-describe this whole situation, but instead I'm going to visualize it using a pressure temperature phase diagram. So consider the case where we have this, where we have in our phase diagram, in one region of the phase diagram, we have the alpha phase, could be the solid, and in another region of the phase diagram, we have the beta phase. Okay? All right, in order for the chemical to exist in this alpha phase, and only in the alpha phase, what has to happen is that the molar Gibbs energy of the alpha phase has to be less than the molar Gibbs energy of the beta phase, right? The Gibbs energy is more minimized if it only exists as alpha rather than it existing in the beta phase. And so if you're in this region at this pressure and temperature range, G alpha ends up being lower than G beta, so the system only exists in the alpha phase. Similarly, in this region of the phase diagram, in the beta region, at those pressures and temperatures, G beta ends up being less than G alpha. As such, because the beta phase has a lower free energy, the system only wants to exist in the beta phase. And then, if you're on the black line, that coexistence curve between the two phases, what that means is that at those temperatures and pressures, G alpha is equal to G beta. And because these free energies are equal, that means both the chemical could exist either in the alpha phase or in the beta phase. All right? And so that's what all that math we went through, that's what that means. And that's why it's very useful to visualize all this stuff using a phase diagram, because it communicates all this information in a very compact form. Okay? Now, I've kept this discussion kind of general, right? I've just kind of said G alpha and G beta. But, of course, we want to be able to quantify and predict the phase behavior of our chemical species. And so what that motivates us to do is to try and figure out how we can quantify and predict the values of G alpha and G beta. How can we actually calculate them? How can we actually model them? All right. And so to do that, what we need to do is we need to go back to the fundamental equation of the Gibbs energy. At the fundamental G equation. Okay? All right, and so fundamental G equation, if you do your thermodynamic square, you see it's this. Where partial derivative of G with respect to T at constant pressure is equal to negative entropy, and partial G with respect to pressure at constant temperature is going to be equal to molar volume. Okay? And so what's useful about this is this entropy here describes the temperature dependence, or tells us that the temperature dependence of our molar Gibbs energy is going to be related to entropy, and the pressure dependence is going to be related to the molar volume. And so if we could somehow figure out the molar volume of our system and somehow the entropy of our system, then we would be able to figure out how temperature, or how pressure and temperature affect molar Gibbs.